Yeah, so actually before I start, let me, because some students were asking me about references and so on. So before I give the outline of my lecture, let me say two references. So there is a very nice review by Compare and his student Firucci. It appeared in 2018 and now published in Lecture Notes in Physics in this volume. So chapter 3 of this review has very good discussion of null infinity and basics of Bondi-Sachs formalism. And there is a more detailed review which talks about connection to conformal infinity and various other approaches. This is by Jeffrey Winokur and Thomas Madler. They are both very well-known people in this subject. This review came out in 2016 and is published in this Scholarpedia. Okay, so here is the outline of my second lecture. I will review a few things I said yesterday. So I will start by a discussion of gravity in Bondi gauge. Then the mass aspect I have already discussed. Today I will discuss the angular momentum aspect. And I will combine this discussion with the equation of motion analysis. So because many of you were asking yesterday about the equations of motion, so I will combine the two things in a right set of ways so that you see how the equation of motion analysis works and how these functions come out. Okay, so this will be the end of the sort of the elementary Bondi-Sachs formalism in a way. Like I am after the first part, I am done with the radial direction. Then I will discuss boundary conditions in the U direction. Okay, so this is the thing which are sort of more modern, and these are the things which people are discussing these days. Then I will discuss asymptotic symmetries, super translations, and Lorentz symmetries is what I will focus on. And finally, I will discuss modern topics that people are discussing on the archive. In particular, Bondi-Sachs formalism in De Sitter is one such topics. Then I will end with my conclusions. Okay, so is everything okay? People can hear me properly?
Yes, I think you can. Yeah, go ahead.
Okay, great. Okay, so let me start with the where I sort of ended yesterday. This was the last set of slides I had in the previous lecture. So I said that when we write the metric in Bondi gauge, we are using u, r, theta, phi coordinates, and we use 4 gauge conditions. 3 of these gauge conditions are these. So GRR is 0 and GRA equal to 0. Okay, and the determinant of the sphere part of the metric is said to be r squared times some function of theta and phi. So these 4 conditions completely gauge fix the metric. And if you can bring a metric into this form everywhere in your space-time, then you are in Bondi gauge. Okay, everywhere. But many people were asking, is it easy or is it difficult to bring this? It's very difficult to bring a given arbitrary metric into this gauge. Even for Kerr solution, if you try, this is a lot of work. Although it has been done, but for Kerr solution, this is a lot of work. Okay, so, but this is just a gauge choice. You can do this not for Kerr solution. You can do it for any solution. You can take Kerr anti-de Sitter, Kerr de Sitter, whatever solution you want, you can try to bring this in this gauge. But now on top of that, we want to use some properties of Einstein's equations and some physics inputs. So we say that I'm interested in studying asymptotic flatness in Bondi gauge. Okay, so I'm looking at asymptotically flat spacetimes in Bondi gauge. Now, Minkowski space in Bondi gauge has this property that GUU is -1, GUR is -1, GUA. There are no cross terms between angles and the U coordinates. So GUA is 0 and GAB is R squared times the round metric on the sphere. So this gamma AB is the round metric on the sphere. So this is the right-hand side of these equations. These are the components of the metric components of the Minkowski metric in Bondi gauge. So now we expect the asymptotic flatness definition to be something of this type, that when we take the limit r going to infinity, this should become -1, this should become -1, this should become 0, and this should become r squared times gamma AB. So this is our naive expectation. And yesterday there was a lot of discussion on this point. A detailed analysis, which was not done over one night. This analysis was done over many papers, and it took many years. There are like 13 papers that Bondi and co-authors wrote in order to sort of finalize this sort of discussion. So a detailed analysis shows that these are the correct boundary conditions to use. So UU component should be -1 plus something which corrects the metric at order 1 over R. So this is capital O, order 1 over R. GUR doesn't have 1 over R component. GUR has 1 over R squared component. GUA has order R to the 0 component. Okay, this might be a bit different from what your expectation is, but this is the correct thing to do. If you don't do this, then there are other problems. So this is the correct thing to do. And GAB is indeed R squared gamma AB plus some correction of order R. Okay, so now this is what I wrote in the previous lecture. In our previous lecture, we wrote that the Minkowski metric is this, and then in Bondi gauge, these are the correction to leading order. So there is 2m over r du squared, then r times CAB dxa dxb, and then this is this cross term, GUA term. This comes because of the equation of motion analysis. You don't have a choice, because if you want CAB to be non-zero, then this must also be non-zero. Divergence of CAB du dxa. Okay, and today's lecture will be about the dots. We are discussing the subleading terms in the expansion. Okay, but before we go into the subleading terms, if you want to get something out of these lectures, then CAB is the most important quantity. CAB is the quantity that carries every information about gravitational waves in this Bondi-Sachs formalism. The U derivative of CAB is the news. It has 3 names: news tensor, Bondi news, or Bondi news tensors, whichever you call it. So I just call it Bondi news tensor. It's the longest possible name you can get. Bondi news tensor. This contains information about what happened in the spacetime dynamically. So at null infinity, NAB contains information about flux of gravitational wave, energy of gravitational wave, angular momentum carried by gravitational wave. All of this is in this NAB, which is essentially in CAB. Okay, so the second most important quantity is this function m. This is a function of u and the theta and phi. So the notation is xa is theta and phi. This is called the Bondi mass aspect, or simply the mass aspect. What this is telling you is how much mass is in different directions of your spacetime. The integral of this function will give you the Bondi mass. And since many of you were asking about the equations of motion analysis, before I introduce the angular momentum aspect, let me say a few things about the angular momentum, about the equations of motion analysis. So let me say a few things about this before going further. Okay, so the way we do this, so the basic idea is that we analyze Einstein's equation in a very specific order. If we analyze the Einstein's equation in this particular order, then the analysis becomes sequential. You solve first equation, then you solve the next equation, you solve the third equation, and so on. And if you do this in this order, the things are very simple. But if you just enter into Mathematica and find the total Einstein tensor, it will look completely hopeless, and it will not be clear how to even go about analyzing that expression. Okay, so this was all done by Bondi and collaborator, and later improved by other people. This discussion in particular was improved by Vinicure in one of his later papers. Okay, so here is the summary. So what we look at is, instead of looking at the Ricci tensor equal to 0, we look at the Einstein tensor equal to 0. So GAB, RAB minus half GABR. The first constraint is the radial constraint, GRR equal to 0. So when you put GRR equal to 0, you will get an equation with derivatives containing R. Those derivatives, if you try to do the expansion of various quantities, beta, V, UA, these are the functions I introduced yesterday. If you do the expansion for those functions, this equation will fix your beta in expansions in powers of 1 over R. Similarly, if you look at the cross constraints, GRA equal to 0, these equations will fix your UA. So I will give examples of both these in the next slide. If you look at the UR equation, this equation fixes V. So of course, as you can see, I mean, this is impossible to remember, but you look at a paper, and the key point I want to emphasize is that there is a sequence, there is a specific sequence in which you have to do this analysis. If you do the analysis in this order, then things are quite manageable and quite simple. Now, once you have GUR equation fixed, it's very interesting to see that GUR equation is same as analyzing the trace of R equal to 0. And the way this comes about is quite interesting. So it comes about like this. So GUR is Ricci tensor UR minus half of the UR component of the metric times the Ricci scalar. Now look at the Ricci scalar. So Ricci scalar in Bondi gauge is UR, this is the contraction that will appear, and RR contraction will appear, and RA contraction will appear. Okay, but these are the two equations that we have analyzed in our step 1 and step 2. So these were these equations, GRR and GRA. So if you use those equations, then you see this is just UR and RAB. Okay, but since we are interested in studying UR equation, everything is equal to 0. So this is essentially the same as studying equation with the GAB RAB equal to 0. So this step 3 is same as GAB RAB equal to 0. So the key point I wanted to emphasize by this little discussion is that as you do expansions of Einstein's equations, there are many such identities that one may need to use. So it may happen that the third order expansion of this equation is closely related to the second order or third order expansion of this equation and so on. So there are close relations between these various expansions, and these expansions one has to keep using in order to simplify the analysis. Okay, so now moving further. So if you want to analyze the other equations, let's say GAB equal to 0, then this GAB equation, it is best to split into the trace and the trace-free part. So the trace-free part is this, and the trace part is this, and the trace-free part is this. Okay, so now I'm not going through this analysis, but again, a simple analysis shows that these equations are automatically solved due to Bianchi identities of the Riemann tensor. So one doesn't need to solve these equations essentially. So we can skip the step 4 and we call it step 4 prime. So now you see what has happened. So out of 10 Einstein's equations, we have already solved these many of them. So the RR equation we have solved, RA equation we have solved. So RR equation fixed beta, RA equation fixed UA, RU equation fixed V, and AB equation did not fix anything. They are just automatically satisfied. Now there are 2 equations left. Let us do the counting. So 1 equation here, 2 equations here, 1 equation here, and 3 equations here. So 3 plus 1, 4, plus 2, 6, plus 1, 7. So seven equations we have analyzed, only 3 are left. And those 3 equations are UU and UA. Okay, so I call this logic to be step 4 prime. And then the UU equation will tell you how the Bondi mass aspect is evolving. So this is the equation that will tell you how the Bondi mass is changing in your spacetime. And UA equation will tell you how the angular momentum aspect is changing in your spacetime. Okay, so now I will define what this angular momentum aspect is, but I gave an overall picture of how these equations get organized. So if you analyze this in this order, then first you solve for beta, then you solve for UA, then you solve for V, and then you solve for the MU dot, M dot, and finally for the NA dot. This is the logic. So if you analyze the equation in this specific order, the analysis is very manageable. I will come to the angular momentum aspect in a moment, just to give an example. Okay, so here is an example. So if you analyze the first equation and do the expansion of this function beta in powers of 1 over r, then asymptotic flatness requires beta 0 to be 0. Einstein's equations will tell you that beta 1 is 0. Then beta 2, Einstein's equations will tell you, is related to the CAB, the quantity that determines the Bondi news in this way, minus 1 over 32 CAB. Okay, so like this is how it happens. So now let's look at another example. So this is UA equation. So UA has an expansion in powers of 1 over r. So this is the 0th component, then the first component, the second component. Second component meaning in powers of 1 over r. The asymptotic flatness requires the UA0 to be 0. if you analyze Einstein's equations, you will see that UA1 turns out to be 0. UA2 turns out to be divergence of CAB. This is what I said in the previous lecture, one of the earlier slides here. You see, when I was saying that the cross term is divergence of CAB, this is that equation. The minus signs are there because the U has a minus sign. And then if you analyze the next order equation, you get an arbitrary function, exactly like you got the arbitrary function in the expansion of V. So here you get an arbitrary set of functions. These are called NA. So U3A has NA and then some other term which is related to the C field. So NA are the integration constants in R, but their functions are U and X. And this is called the angular momentum aspect. Okay, so these are the four physical quantities in Bondi expansion. So one is CAB. CAB is the thing that carries information about the gravitational wave. M is the Bondi mass, which contains information about the mass of your spacetime. And NA is the information about angular momentum aspect of angular momentum of spacetime. So there are two components, n theta, n phi. Okay. Similarly, the V equation has this kind of expansion, -1 + 2m over r. M is the Bondi mass, which I discussed earlier. Okay, so now finally we are left with three equations because all the expansions are solved, all the arbitrary functions are obtained. Now the last step will give you the evolution equations for the Bondi mass and angular momentum aspect. So finally we have the equations for the evolution of the mass and the angular momentum aspect. So del U of M equal to something and del U of NA equal to something. This is where all the physics of, most of the physics of Einstein's equations are. These are the evolution in time. These are the, okay, so in asymptotically flat spacetimes in vacuum gravity, these equations are not very difficult to write. I can write them in just 2 lines. So the equation tells us that del U of M is a double derivative of the New's tensor. And here the derivative of the angular momentum aspect is related to some sort of double derivative of the C function, the C tensor. Yeah, C tensor doesn't have a name. It's perhaps the most important quantity, but doesn't have a name. The N tensor has a name, Bondi News, but C doesn't have a common name. Okay, so why the name angular momentum aspect? The name angular momentum aspect because it is closely related to the angular density of the angular momentum with respect to the origin defined by the Bondi coordinates. So Bondi coordinates naturally define some origin r equal to 0. With respect to that origin, the spacetime carries angular momentum, and the integral of n will tell you what is the angular momentum. Okay. So now there is a lot of discussion about what is the meaning of angular momentum, and there are many papers on this. I will not go, this is not the place to go into those details. This is a pedagogical lecture. So let me just say that roughly speaking, if you just do the integral of n lower component phi over the angles, then you will get your the total angular momentum of the spacetime. Okay, so for the experts, like this is not the correct formula. There are other terms in the formula, and there is a lot of discussion about those other terms in the formula. But I think if you are seeing this for the first time, then I think this is good enough that you take the angular momentum aspect and do the integral over the sphere, you will get the angular momentum of the spacetime. Okay, so let me make a summary of all this. This might be a bit technical for people who have not seen this, or maybe technical for people who are not interested in this, but let me just make a summary. So as you can see, this part of the analysis is tedious, lot of calculations are required. But the key point that I wanted to say, and this is what I emphasized in my previous lecture also, the whole analysis is very hands-on. You can give it to a student, and student can program these things and compute all the equations in powers of 1 over r expansion. Okay, there is no fancy mathematics involved. There is no difficult differential geometry. It's just covariant derivatives you write in terms of the sphere derivatives. It's just very long and tedious calculations. There is no, in my opinion, there is no very fancy math and no difficult differential geometry. So as far as the expansion in powers of r is concerned, once you put things in Bondi gauge, you make some choices about how to expand these things. You can just do these calculations. Okay, so this is one of the main message I wanted to give from my lectures. Okay, so this is all I wanted to say about the radial expansion. Now I will go into more detailed discussions of other things. Yeah, so this is a good place to stop for me to take questions. Actually, this is the part that I really wanted to convey from my lectures. So if people have questions, comments on this point, I will be happy to take now.
So if you have questions, please unmute yourself and ask.
Okay.
Okay, so there is one question in the chat box. Maybe I can repeat.
Yeah.
So, I mean, I'm not sure. Okay, Sayantan Ghosh, are you there? Can you please just ask it? Sayantan? So I'm not understanding his question. Sorry, my mic. Okay, his mic is not working. So his question is something. Is it like the
common integral in the ADM formulation? Yeah.
Yes.
Yeah. So in fact, so this is something I discussed briefly in yesterday's lecture, but I will discuss more in the today's lecture. In the u going to minus infinity, the angular momentum expression will indeed become the ADM angular momentum. And as you said, the ADM angular momentum is closely related to common integral. So indeed, one can make all these connections. Yeah. But this is only in the u going to minus infinity limit. Okay, thank you. Yeah, okay.
Okay, so is there any other questions? Okay, maybe you can continue, Amitabh.
Okay, thank you, Deva Prasad. Okay, so this is all I wanted to say about the basics of Bondi-Sachs. Now I'm moving into more research directions. Okay, so boundary conditions in the U direction. So this is one topic which is much discussed in the literature over the last few years. Okay, so physically, what is happening? So let us consider a class of spacetimes where the solution starts from flat space in the far past and goes back to flat space in the far future. Okay, so this is a situation. You have Minkowski space far in the past. So m, the Bondi mass in the v going to minus infinity limit is 0. Then some sort of gravitational wave comes. Maybe the space-time has some mass, and then this gravitational wave scatters and goes to infinity. Okay, so this goes to infinity. So in the end, m at u going to plus infinity is also 0. So in between there is a mass. So here the mass is 0, here the mass is 0, but in between there is some mass here, there is some mass here. The mass is changing as a function of v, as a function of u, and so on. Okay, so these classes of spacetimes, so consider all such spacetimes which are possible. These classes of spacetimes have been favorite for mathematical minded relativists, and they can be dealt in a very rigorous way. These are called Christodoulou-Clairamin spacetimes. Okay, so these are very popular in mathematical GR literature, and you will see why they are popular in the physics literature in a moment, just 3 lines below. So a study of these spacetimes reveal that the following boundary conditions in U are satisfied by this class of spacetime. Okay, so this is the analysis done by these mathematicians. What they have shown is that the News tensor falls off like 1 over U. Any power higher than 1 over U, as you go, U going to plus minus infinity. So that is to say, as you approach this spatial infinity point, that is the case when U is minus infinity, and as you approach here, U going to plus infinity. In all such situations, in both these situations, in fact, is true for the past also. In all such situations, the News tensor falls off as 1 over U, a power higher than 1 over U, such that this space-time has asymptotic flatness in the past and asymptotic flatness in the future. And I mean, they remain Minkowski-like everywhere. Okay. not only the NAB falls off like this, the Bondi mass function, the M and NA remain finite everywhere. So M and NA have finite limits as U goes to plus minus infinity. So there can be some mass in this spacetime. So the ADM mass of this spacetime can be non-zero. So they may have some ADM mass, but the amount of, since the new tensor tells us about how much energy the gravitational waves are carrying. So the amount of energy gravitational wave carries in this very little region near spatial infinity, that is very small. In fact, zero in the U going to plus minus
Okay,
infinity.
Amitabh, just because it's the question that somebody asked it in the chat box, the question is very relevant at this point. That is why I just interrupted you. Sorry for this.
Yeah.
So the question is, because your gravitational wave going in and then scattered going to the infinity. So question is, I did not get what happened with that mass, because mass is equal to energy. So that was the question. If you look at the chat box.
Yeah. No. So of course, the mass is equal to energy. I mean, but the mass can be carried by different type of particles. Mass can be carried by. Okay, first one has to make a distinction between the ADM mass and the Bondi mass. ADM mass is the mass that tells you about the total mass of the space-time, like the gravitational waves in the space-time, the black hole in the space-time, stars, all those things are captured by the ADM mass. The Bondi mass is telling you the dynamical mass of the space-time. As the space-time is evolving, some gravitational wave is coming out. So it is telling you how much gravitational wave has come out in a way. So like if you calculate this is something I discussed yesterday. So if you calculate mass at point U2, then mass at point U2 is mass at point U1 plus the amount of flux of gravitational waves that has come out. Okay, so the mass is equal to energy, that statement is true. But okay, now there is one more technical question. What is the distinction between Misner-Sharp mass and ADM mass? Okay, let me first make a general comment. So the general comment is that there are many definitions of mass in general relativity. The there is a canonical definition which is based on the Hamiltonian methods. So the generator of time translation defines a notion of a Hamiltonian, and that Hamiltonian defines a notion of mass. So that is called the ADM mass. The Misner-Sharp mass, I do not know exactly what the definition is, but in situations where this mass can be compared to ADM mass, I would think that this agrees with the ADM mass. I mean, there are hundreds of definitions of mass in general relativity. There is no end to this. Komer mass, Ashtekar Hansen. I mean, there are many definitions. So, but there is a canonical definition which is the generator conjugate to time translation, and that's what we mean by the ADM mass. And I'm quite sure that this Misner-Sharp mass, most likely it corresponds to the spherically symmetric setup with dust or something like this. I have seen this definition somewhere. But in the context of our situations, it will be equal to the ADM mass. Okay, so are there other questions?
No, I think there is no other. So you can just let me see. Yeah, you go ahead. Yes.
Okay, so this was the work of these mathematicians. They are very famous mathematicians, but now physicists have to do something more. So what we do is that we just jump. So physics jump. Okay, so this may be a wild jump. Mathematicians may not like it. Okay, but that's fine. So what we do is that we do not expect this fall off to change even in the black hole spacetimes. Okay, one can debate whether this is true, not true, correct, not correct, whatever. But this is the jump that we make, and then we try to make some progress. So that is to say, we expect these boundary conditions to be good boundary conditions even when the black hole forms in the space-time. Okay, so with these boundary conditions, with these assumptions, one can do a number of things. So here is an example. So since the Christodoulou-Clairaut space-time have this property that the Bondi news goes to 0 as U goes to minus infinity, we just put this in this equation and we observe that del u of m goes to 0 as u goes to minus infinity. Okay, that is to say the mass of the spacetime becomes constant as u goes to minus infinity. Okay, so the mass of the spacetime has become constant in this limit. Similarly, from the other side, the mass of the spacetime will become constant from past null infinity. And then one can ask whether the mass defined at past null infinity matches with the mass defined at future null infinity. Okay, so this is some question one can ask. And this is one question that has attracted a lot of attention. And people have tried to use matching of physics at past null infinity to physics at future null infinity. Okay, and this is based on this physics, essentially based on this physics jump, which takes these boundary conditions even for black hole spacetimes. Okay, so I will give you another example. So another example is this. So I said that the angular momentum aspect, the u derivative of the angular momentum aspect is given by this function. Now, if one do the analysis for Christodoulou-Clairaut spacetimes, and assuming this physics jump, then a separate analysis shows that del u of NA also goes to 0. Okay, this argument is different from this argument, but a separate argument shows that like the del u m goes to 0, del u of NA also goes to 0. That is to say the angular momentum aspect becomes constant in u as you approach u equal to minus infinity. Now, this would imply that the right-hand side of this equation becomes 0. So you see, this is a condition on the C function now. So if this quantity becomes 0 at u going to minus infinity, then you can say something about the C function, the C tensor. And remarkably, it turns out that if this equation is satisfied, the C function is specified by a scalar function. The C tensor is specified by a scalar function now. So this equation implies that the CAB is derivatives of a scalar function C and some Laplacian acting on the function C. Okay, so C is a scalar function on this sphere. So as a result, what has happened is that given this physics jump, what has happened is that on the null infinity, there is this new tensor, NAB, and at the place where it meets spatial infinity, you have these three quantities now. So you have M, the Bondi mass aspect, which has no dependence on U anymore because you are at U equal to minus infinity. The N only has dependence on the coordinates, U dependence has gone. And because of these U dependence being gone, the CAB tensor has reduced to just one function C, okay, which is defined at past of the future null infinity. Okay, the same is true for the other side. Okay, so this is the future null infinity. The same is true for the past infinity. So scribe plus, you have these three functions now. Four functions, and at scribe minus, you have these functions: C of xa, M of xa, NA of xa. So a key question that has attracted a lot of interest in the last 10 years is the relation between these quantities. What is the relation between the C function at past null infinity, the future of the past null infinity, to the C function at the past of the future null infinity? The relation between C function at this point to the C function at this point, the mass functions and so on. Okay, so this relation has been explored through spatial infinity, and many papers have come out on this subject. Okay, so now this is all I wanted to say about the boundary conditions in the U direction. I am happy to take some questions here. Yeah, so Indranil has a question. What happens when you couple matter? No, is there similar fall off like Bondi news? Yeah, indeed, one can do this analysis with matter coupled. In the references I mentioned, there are comments, and then from the references, you can find the papers. With matters, the analysis is much more detailed. As I was saying in the previous lecture, there is this art and science balance. So what kind of boundary condition you want to allow for the matter, this will change the boundary condition for the metric, and then you have to find the right balance. So there is a lot of richness that one can explore. Okay, very good. How I am doing in time? I have only 20 minutes or so left. Okay, so let me continue. It doesn't matter how much I mean, it doesn't matter if I finish my lecture or not. I will just say a few things and then stop. Okay, so the next topic I want to discuss is asymptotic symmetries. So what do we mean by asymptotic symmetries? So asymptotic symmetries have some complicated definition, you can say, like it has some definition in terms of Hamiltonian charges and so on. We will come to that in a moment. We are asking a simpler question. What we ask is, what are the vector fields that preserves the Bondi gauge and the boundary conditions that we impose? Okay, so try to understand the question. So we have uh, metric written in Bondi gauge, and we have imposed some boundary conditions on the metric based on some physics inputs. Like we want to allow for gravitational waves, we want to study the energy of these waves, the energies should be finite and so on. So we have put some boundary conditions on our fall-offs. And now we are asking the question, what are the vector fields that preserve this Bondi gauge and the boundary conditions? Okay, so let us just make them equations now. So the Bondi gauge is GRR equal to 0. So I want to look for vector fields such that the Lie derivative along those vector field of the GRR component is 0. So similarly, GRA is 0. So Lie derivative of GRA along that vector field should be 0. And the radial coordinate has to satisfy this determinant condition, that determinant of G, this is the metric on the sphere. So determinant of the metric of the sphere divided by R squared is only a function of theta. So I can write it like del R of this quantity is 0. So the Lie derivative of del R of this quantity must be 0. So these are the three conditions which are sort of just preserving the Bondi gauge. Okay, so now we have the boundary conditions also. So the boundary conditions were GUU falls off like 1 over R. So the vector field should be such that the Lie derivative of GUU should also be 1 over R. Okay, otherwise the boundary conditions will change. So we don't want that to happen. So the vector field should be such that they should preserve the boundary conditions. So GUU must be, or Lie derivative of GUU must be 1 over R. Okay, similarly for the other cases. So the UR falls off like 1 over R squared. So the Lie derivative of UR should be 1 over R squared. Lie derivative of UA should be R to the 0. And Lie derivative of GAB should be R to the 1. The third condition you don't have to write in a covariant form. This is a scalar quantity. Lie derivative on the scalar quantity is just zel mu, xi mu, del mu. So you don't have to write it in a covariant form. This is a scalar quantity, is a covariant quantity. Yeah. Okay. So now this is a bit of a jump. I cannot explain this in real time. So you see, so you have a lot of equations now. So you have this Lie derivative equations. So 4 equations coming, I mean, number of equations coming from here, number of equations coming from here. You can write all these equations in partial derivatives and analyze them. It will take you maybe 2 hours or 3 hours to analyze what are the conditions all these equations are imposing. But believe me, this is not a difficult exercise. You just write all these equations and analyze which component of which vector should be what and so on. If you do that analysis, a calculation will show that the following vectors preserve the Bondi form and the fall off. The following vectors preserve the Bondi gauge and the boundary conditions. So let me explain what these vectors are. So these vectors depend on 2 functions. So one function is capital T and the other function is a vector actually. The other is a capital vector R. So RA. The U component of this vector, the partial U, the U component of this vector depends on the functions like this function T appears and the derivative of this R appears. Okay, and then there are corrections. Corrections are to order R to the 0. Okay, this is the little o notation which I reviewed in the previous lecture. That is to say, the corrections start with at least 1 power of R. 0 power of R because R to the 0. Okay, then the angular part is RA. So you see, so the way these functions are defined or designed are precisely this, that the U component should be T times del U and the angular component should be RA times del A. And then there are corrections. So 1 over R DAT, this correction is coming because of the T. And the R component of the vector has various things which are constructed out of derivatives of the functions T and the vectors R. The key point, the details are not so important. I mean, once you understand what this is, you can substitute this in Mathematica and check whether the boundary conditions are satisfied, gauge conditions are satisfied. So checking this is also not very difficult, easier than finding them, but finding them is also not very difficult because there are many equations you have. So all these equations you just analyze in some organized way and you will get this answer. Okay, the key point is that there are arbitrary function, at least one arbitrary function that appears in this analysis, and this is called the super translation. So T of XA is an arbitrary function which appears in this analysis. This is called the super translation. The name super translation, we will explain why this is called super translation. The other function that appears is this vector, sorry. The vector that appears is this RA. So this is a vector on the sphere. And this vector obeys conformal Killing equation on the two-dimensional sphere. So dA/RB plus dB/RA is gamma AB dC/RC. Okay, so if you restrict yourself to smooth vector fields, okay, this is what I will do in this lecture. If you restrict yourself to smooth vector fields, then these R's are the Lorentz generator. So there are 3 rotation killing vectors and 3 boost conformal killing vectors. So 3 plus 3, 3 rotations, 3 boost, and they form the 6 generators of Lorentz group. And they are all solutions to this equation. On the sphere, they are the solutions to this equation. Now, to simplify our life, we consider R equal to 0. Okay, we are not doing any rotations or any boost. So just putting T. So just look at T, the super translations. If you just look at T, the vector field is this. So zeta of T is T times del U minus 1 over R divergence of T and 1 over 2 Laplacian on T. This is in the R direction. This vector field preserves Bondi form. It preserves asymptotic boundary condition in a way such that when you apply this, the asymptotic fields change. Okay? The boundary conditions are preserved, but the asymptotic field changes. So one can write down how this vector will act on various quantities. One can write down how it will act on the Bondi mass. One can write down how it will act on the angular momentum aspect, how it will act on the C tensor, and so on. So all those formulas you can find in the reviews that I mentioned. Perhaps what is very interesting is that this is the only formula that I have written here for the action of the super translation field on the super translations on the asymptotic field. The scalar field that I discussed, okay, the CAB becomes derivatives of the scalar. So the action of super translation on the scalar field is very simple. Just delta T of C is T. Okay, this is just this. Okay, so now why are they called super translations? What you can do is that you can take partial Z, like translation in the Z direction, and you go to radial coordinate, convert into r theta phi, and then you convert into u r theta phi coordinates. If you do that exercise, you will see that this form is what partial Z takes. Partial Z will be like cosine theta del u minus 1 over r divergence of cosine theta del a plus 1/2 Laplacian acting on cosine theta del r. Okay, like this. Similarly, if you do for partial x, you will see that it takes this form with various terms given by this equation. So for translations, you see that, I mean, with this small calculation, you see that for translations, the vectors takes this form. And since this is a generalization of our translation, because T is an arbitrary function, these are called super translations. Okay, so now one can construct charges for various these symmetries. Let me not go. Okay, so the charges in general relativity is a big subject in itself. I mean, one can give many lectures on this. I will just try to be very simple. So I will just say that the super translation charge Q of t, the first variation of that charge is given by first variation of this quantity. And then there is this term which cannot be written as delta being pulled out. So you cannot put the delta here. The delta has to be inside here. So this is the non-integrable piece. So this is the integrable piece. Here you can pull out the delta, but here you cannot pull out the delta. So this is the non-integrable piece. This non-integrable piece tells you about the flux of super translation charges. How the super translation charge changes when you go from one point to another point at null infinity. So here is the picture. So if you go from point 2 to point 1, there will be some gravitational radiation coming out. This gravitational radiation may carry super translation charge, and the change in the super translation charge will be captured by this expression. So this is the Bondi news multiplied with the CAB. Okay, but when you go to spatial infinity, then as we discussed, the News tensor goes to 0, and then this becomes a total charge. You can remove the delta. So if you remove the delta, then Q super translation charge is just the integral of the super translation T against the Bondi mass M. So it's just the T times the Bondi mass M. So what this is telling us is the moments of the Bondi mass. The super translation charge captures the moments of the Bondi mass at spatial infinity. Okay, so this is something I discussed. So QT2 is QT1 minus flux through the future null infinity. Similar formulas one can write at past null infinity, and then one can ask whether this expression matches at future and past. Okay, so again, this is some topic that people have worked on a lot in the last few years. Okay, now let me briefly mention about the Lorentz algebra. So Lorentz algebra has t equal to 0. Only the vector field r is non-zero now. For the vector field r non-zero, this is the form of the vector field that preserves the Bondi gauge and the Bondi boundary conditions. So see, this is RA del A. This is why it is a rotation. I mean, R phi del phi, the simplest case will be just del phi. And then the radial part, the vector has some radial part which is related to derivative of the vector r, and then it has some u part which is also related to the derivative of the vector. And as I said earlier, these vectors satisfies the conformal Killing equation on the two sphere. So there are 6 solutions, and these are the 6 generators. Okay, so together with the Lorentz symmetries and super translation, what we have is something called BMS4. So this is the Bondi, Meissner, Sachs group. 4 because in the literature now people are discussing BMS in different dimensions, BMS3, BMS5, BMS6, whatever. And this is the canonical BMS group. Okay, there are many generalization of this. The generalization I'm not discussing in this lecture. But this is the old canonical BMS 4 group. Okay, B. Okay, so now this is essentially all I wanted to say. So now I have a few slides on modern developments, but I'm happy to take questions and yeah.
Yeah, there is one question. How is the third written in the covariant form? I'm not sure which one he's talking about.
Yeah. No, this I answered. This I answered. So this person was referring to this derivative condition, the Lie derivative acting on the derivative. So
Okay. Understood.
the physical quantity the super translation charge correspond to. This is a difficult question. Um, okay, for translations, it corresponds to the momentum. So translation charges are momentum, and we understand what the physical interpretation is. Now, for the more general super translations, the physics understanding is not so obvious. What people have discussed is that this super translations correspond to some memory effect. But that is some topic that I will not discuss in this lecture. I have not prepared slides on that. Yeah, so the physical interpretation of supertranslation charges is not completely straightforward. Okay.
If there is any questions, please you can unmute and ask directly.
Hello, sir.
Yes,
I have a question.
Yes.
So, can you tell more about the news tensor? Means actually the gravitational waves are carrying the information, right? Means
yes.
from horizon to null infinity. So at null infinity, is there any receiver who is receiving that, or like?
Yeah, exactly. So what will happen is uh, uh, maybe this diagram is better. Yeah, this diagram. So suppose you have a detector at u equal to u2. So at this location, you will measure, let's say, the Bondi mass, and you may ask, can I compare this at location u equal to u1? So the idea is that the difference between the Q2 and Q1 will be given by the integral of the news tensor. It will be related to the integral of the news tensor along this U2 minus U1 length of this null infinity. Yeah. So the news tensor actually tells you information about how much gravitational radiation is coming, and using that you can compute the energy of these gravitational waves that are coming.
Okay, thank you.
Hello, can I have one more question?
Yes.
Yeah,
So,
go ahead.
Yeah, so I was just wondering about this boundary condition that you have taken,
Yeah.
which also, gives rise this conformal killing equation. Okay, so as we know that there is some extension of BMS group recently that have been achieved.
Yeah.
So this conformal killing equation had also been recovered there probably,
Yeah.
but probably the smoothness of this vector field was relaxed, right?
Yes. So there are multiple extensions people have discussed. Um, One extension discussed by Barnich and Troissard is you look for solutions to this equation which are not necessarily smooth, holomorphic functions on the sphere. Monomorphic. So when we are looking at smooth functions, we are looking at holomorphic functions. But when we look at non-smooth functions, these are meromorphic functions on the Riemann sphere. And people have written many papers on this. There is another set of boundary conditions that people have proposed. People say that you do not set the metric at infinity, the sphere metric, to be gamma AB. You allow that gamma AB to change. And if you allow that gamma AB to change, then this equation has no meaning because gamma AB is changing. So this equation just becomes, some sort of it doesn't tell you anything. So then this gives you an extension of the BMS4, which has been called the generalized BMS, in which you allow for arbitrary vector fields on the sphere to be your asymptotic symmetry. So there are many generalizations people have. There are other generalizations. There are like many versions people have discussed, but all those versions, in my opinion, have one problem or the other. So I don't, that is a sort of a digression from my main lecture that I want to give. So I don't want to go into the problems.
So instead of this conformal killing equation, if one solves killing equation, so you will get three generators, right?
Yeah.
On sphere.
Yeah, but that is too restrictive. You want to, you see, the conformal killing equation comes because you want to have freedom in redefining your u coordinate and radial coordinate and things like those. So preserving the Bondi form, preserving smoothness of the metric at the sphere, this is the equation you will get.
Okay, okay.
Okay, so this is the reason I said I wrote it in capital. This is the old canonical BMS4 group. There are many versions of the new BMS group, which I'm not discussing.
So would you be able to tell something about the conservation of these charges, or I mean supertranslation charge?
I said, yeah. So conservation for super translation charges is not surprising. So the super translation charges at spatial infinity, they are completely integrable, and you can write down an expression for Q of t, which is just t times m. And you can ask whether this expression matches with something at spatial infinity. One can ask whether this matches with past null infinity. All those questions one can address. When you are at null infinity, then of course, since there is a flux, you cannot write down a full conservation. You can write a conservation law, but conservation law is in this sense that you can relate Q2 to Q1 via a part, which is this flux relation. Yeah.
Okay,
Yeah.
yeah.
Ayan is saying, I guess this is Ayan Chatterjee.
Yeah, can you discuss some of the recent things that are going on? So yeah.
Okay. So the subject has received great interest in the last few years. I mean, the subject was considered to be very difficult and exotic 10 years ago, but now like string theorists and relativists and people in between, like all sorts of mathematical relativists, everybody's lot of papers and many people are working on this subject. So these are the 4 or 5 main topics that people are discussing. So one is matching across past and future null infinity. So this is a topic which is of great interest. It's rather surprising that relativists did not address these questions in the 60s when they discovered the Bondi-Sachs formalism. Only very recently, the interest in this subject has started, and a lot of papers and lot of progress. This is some subject that I have also worked on. This is very interesting developments have taken place. Okay, so now as Srijit was saying, there are many extensions of this BMS symmetries, extensions of asymptotic symmetries to all sorts of extensions people have discussed: generalized BMS, extended BMS, holomorphic BMS, like lots of extensions people have discussed. In my opinion, most of the extensions have one problem or the other. So for every extension that people have discussed, you can find a paper which argues that that extension does not make sense. So like there is a lot of discussion in the community on this. There are also extensions in other directions, like extensions in logarithmic directions and so on. Okay, then there is a lot of interest in relation to soft theorems from quantum field theory. Relation between soft theorems and relation to asymptotic symmetry. So this is also subject that has received a lot of attention. People from Chennai have worked a lot on these things. Then memory effect is another topic which has received a lot of attention. This is related to the interpretation of super translations, and as an extension relation to extensions of these asymptotic symmetries also. Okay, so for the interest of time, I will not go into the details of the above topic. There are another topic that has received a great deal of interest in Bondi-Sachs formalism is de Sitter gravity in Bondi gauge. So this is the subject. This is another one of those subjects that I have worked on. So let me say a few things about this here. Okay, so Bondi-Sachs in de Sitter. So Bondi-Sachs formalism famously clarified many aspects of gravitational radiation theory in flat space. Okay, one can say that this was the formalism that led to a lot of development in theoretical aspects of this gravitational radiation theory. Now, it is widely believed that the same formalism can be useful in other spacetimes, in particular in de Sitter spacetime. And in the last 5 years, people have tried to make sense of this, especially after the work of Ashtekar, Bonga, and Keshavan from 2015. Okay, so de Sitter space is like so. And what we are interested in is UR theta phi coordinates. UR theta phi coordinates cover some part of de Sitter space, which is drawn in this lines, by these lines. Okay, so we want to focus on the diagram where future null infinity is there. So this full line is there. And some part of this spacetime will be covered by UR theta phi coordinates. Okay, so what we will do is that we will write the metric in Bondi gauge with the determinant condition. Okay, so there are variations on this. There are other people who have written papers. We do something else. But what I will discuss is we write the metric in Bondi gauge with the determinant condition. Okay, so these are the functions. So the beta is the function which enters the UR component, and the V is the function that appears in the UU component, and GAB is the metric on the sphere, and UA is the function that appears in the cross terms between U and XA. Now, as before, one has to do an equation of motion analysis in a sequential order. This has been done in a great detail in number of papers. Equation of motion analysis reveals that this function beta starts with 1 over r squared. And the u function has more integration constant than you might naively expect. So u function has this ua0, which is not fixed by the equations of motion. The next term is fixed by the equations of motion. And then there is the angular momentum aspect, which is not fixed by the equations of motion. And then there are terms which are fixed by the equations of motion. Okay, so there are two functions that appear here. So UA and NA. So NA is the angular momentum aspect, and UA is the arbitrary set of functions which are allowed by the equations of motion. Okay, so this may look a bit surprising, but there is a very deep physics here. So the physics is that in de Sitter, both normalizable and non-normalizable modes are required to have any dynamics. If you turn on only non-normalizable mode, then of course you don't have any dynamics in de Sitter. If you turn on only normalizable mode, then finally it so happens that there is no dynamics in de Sitter again. So in order to have any sort of gravitational waves or any sort of gravitational dynamics happening in de Sitter, you must turn on a combination of normalizable and non-normalizable mode. And this is the reason both NA and UA appear in this Bondi expansion. So NA is the normalizable part and U is the non-normalizable part. So both these things have to be turned on. Okay, so moving further, so we look at the equation of motion analysis for the function V. So because we are in de Sitter, so there is this lambda term which is related to de Sitter. Then the r square terms is fixed by the U, which we have already said that it is free. And 1 over r, the next term, the r term is fixed by C. Okay, and then a new function appears. This function is as in flat space. This is the Bondi mass aspect. Okay, we carry on. We have GAB. GAB has gamma AB, which we have chosen to be round metric on the sphere. One can relax this, but there are good reasons not to relax this. So gamma AB is the round metric on the sphere, and then there is CAB and further things. If you go down in the expansion, this 1 over r cube term appears. This is the normalizable. No, this should be normalizable. Normalizable modes allowed by the equations of motion. Okay, so as before, the most important quantity is CAB. So CAB now is determined by U. So in flat space, remember, CAB was a completely free independent data that you have to give. Here, it's not the case. The C function, the C tensor is determined by U. So the equation that CAB satisfies is this. CAB is divergence, not divergence, derivative of U, a symmetrized derivative, and there is a divergence here. So you see, this is very interesting. All the information that CAB carried in flat space, I said CAB was the most important quantity that carries everything about information about gravitational radiation. In this context, all the information in CAB is contained in UA0. So CAB is symmetric, traceless, remains an arbitrary function of the retarded times and angles. All that is true, but all the information about C is contained in this U. So U is the correct analog of the radiative field in de Sitter space-time. The news tensor, unfortunately, is not such simple, and unfortunately, still after about 5 years of discussion in the literature, there is still no canonical simple definition for news tensor in the literature. The one of the nicest expression is like so, that NAB is derivative of U, derivative of CAB, and then there are a lot of other things, which is like Lie derivative of CAB in the U0 direction, some divergence of U times CAB, and so on. And if one does the analysis, then one finds the evolution equation for the mass aspect, evolution equation for the angular momentum aspect, but these equations are a lot more complicated, and a lot of things not completely sort of sorted out about what these various terms mean and what is the physical understanding of all of this. This remains to be explored. Okay, the energy is given by the integral of the mass function. So this is very nice. This is how the mass function is defined, is designed. And similarly, the angular momentum is given by the integral of the angular momentum aspect, but this is roughly true. I mean, again, there are subtleties about the extra terms, and for the extra terms in flat space, there are many papers discussing those extra terms. In de Sitter, there are not so many papers. People have not gotten around discussing the angular momentum physics in de Sitter yet. Asymptotic symmetries and other details are essentially research topics. I mean, there are papers which disagree with each other on basic premises. So asymptotic symmetries in de Sitter is indeed unsettled topic. The most important question in this subject is positivity of Bondi flux. This has been partly addressed, but not completely. And if you're interested in this, this is the paper. Beatrice Bonga will give a talk in this conference at the end of the conference. This is from last year, June 2023. In this paper, you can find all the important references on this subject. And this is all I wanted to say. So thank you.
Okay, so thank you, Amitabh, for nice discussion on this difficult topic. I hope students have understood a bit of it. So if you have any questions, maybe 1 or 2 maximum question you can take. So if anybody has any question, please go ahead and ask. There is one question in chat box. Maybe you can look at it. Yeah. Srijit has